Combined arithmetic and geometric change. We start off by looking at the concept of growth and decay. Growth is something getting bigger over time, and decay is something getting smaller over time. And we're just actually going to do a summary of what these look like in arithmetic and geometric sequences. And this actually comes from the table on page 166. So feel free to refer to that. So we use they have different parts. So an arithmetic sequence, A is our first term, and that's the same in a geometric sequence. But D, sometimes capital D, is the common difference. And we use the capital D in our depreciation and percentage change, the money type of things. R, the common ratio. Now you'll remember that we got confused. Little r does mean the common ratio when we're doing just basic geometric change, but sometimes it has to mean the percentage interest rate, which is really annoying. So sometimes, again, this gets called big R. Why we just don't make them capital D and capital R, I don't know, but so be it. It is the common ratio. So remember, arithmetic sequences have a common difference, that's adding or subtracting from every term to the next. Geometric has a common ratio, that's multiplying by an amount from one term to the next. Their recurrence for arithmetic, we say that T1 is A, so our first term is our first term, funnily enough. Tn plus 1 is Tn plus D, that is, each term is the term before it plus the common difference. This is a recurrence relationship. For geometric sequences, we still have T1 is A, but Tn plus 1 is the common ratio times the previous term. We'll separate this out into a little table thing here. So we're comparing how a recurrence relationship looks for arithmetic and geometric. This is a nice overview of what we've done so far. A rule for the nth term. So you'll remember a recurrence relationship is about going from one term to the next term. The rule for the nth term is about finding any position of the term. For arithmetic sequences, this is Tn equals A plus n minus 1 times the common difference. For geometric sequences, this is Tn, any term, the nth term, is equal to A times the common ratio to the power of n minus 1. So we've learnt both of those. This is our nth term rule, this is our recurrence relation rule. They are different things. Now, in terms of growth and decay, an arithmetic term increases when I'm adding a number, that is, when the common difference is positive. It's more than 0, and I'll add a little note there, positive common difference. So a positive common difference in an arithmetic pattern would have a graph that looked like this, and a number pattern that was increasing, 2, 4, 6, 8, or whatever it happened to be. When the common difference is less than 0, that is, it's a negative common difference, then we're taking away from each term, and the graph would look like this, like 10, 5, 0, whatever, moving down the page. For a geometric sequence, it doesn't depend on D, it depends on R, our common ratio. And when our common ratio is more than 1, I get growth. Hang on, we better label these. This is growth. This is decay. Not decaf, decay. This is going to be growth. Common ratio of more than 1. Now our graph, you'll remember, isn't linear for a geometric sequence. It would curve up. If our common ratio is between 0 and 1, we would get decay. We don't deal with negative common ratios in this course because it's too tricky. But this is common ratio. Basically, it's a fraction, less than 1. And that geometric decay would look like this. I'll even put that on the screen for you so you can see it. So arithmetic growth, straight line up. Arithmetic decay, straight line down. Or linear growth, linear decay. Geometric growth, curving up. Geometric decay, curving down. That's an overview of the difference between arithmetic and geometric. Now what we have to be able to do is combine the two, because some patterns have combined arithmetic and geometric growth and decay. We are going to have a recurrence relation for this sort of thing. So the sort of situation you'll get is if, say, something is going up or down by a percentage, but there's also a fixed amount being added or subtracted in, like a bank account, where there's a percentage interest rate increasing, but you're also taking out $500 every single month. Taking out $500, arithmetic. Increasing by a percentage, geometric. They can both happen in the same thing. So, we use V for value or T for time, whatever they tell you to use, you use it. There's a capital letter. V0, starting value of the sequence. We use little r, percentage change. Capital D, amount of arithmetic change. And remember our definition of capital R. For growth, it's 1 plus the percentage change on 100. Or for decay, it's 1 minus R on 100. So this is, remember how we use capital R and little r differently. I've got growth and decay. And our recurrence relationship is V0 for the starting value, Vn plus 1 is the common ratio times the previous value plus D. Now sometimes if D happened to be a negative, we'd write negative in there. So let's see how this works. Each day, 1.4% of the water in a swimming pool is lost to evaporation. That's a percentage of the current amount and it's lost, so this is geometric decay. At the end of each day, 1,000 litres of water is added. That's a fixed amount and it's added. That's arithmetic growth. 150,000 litres in the pool, that's our starting value. Hope you can read my blue pen, sorry, I'll switch to something more visible. And they've defined what letter they'd like you to use. We'd like us to use WN to be the amount of water left in the pool after n days. 1, write a recurrence relationship. W0, starting value, is 150,000. We have to work out capital R and capital D. Geometric decay means this is our R. So we'll do some working out over here. R is 1 minus little r on 100, which is 1 minus 1.4 on 100. Use your calculator if you need to. Our common ratio is 0.986. We need to find D, the amount of arithmetic change. D is 1,000, and it's plus 1,000 because it's arithmetic growth, so it's positive. Then you use your combined arithmetic growth and decay. Vn plus 1 is the common ratio times Vn plus D. Substitute it in. This should be W. N plus 1 is 0.986 times Wn plus 1,000. That's it. That's our recurrence relationship. Use that to find the amount of water in the pool after 3 days. In a big question like this, you probably want to show full working for something like this. So W0, 150,000. W1, the water after 1 day. 0.986 times 15,000, 150,000 plus 1,000, and work out what that equals. Type it into your calculator. 148,900. The amount of water after day 2, 0.986 times the amount that was in there, plus 1,000. Type it into your calculator. The amount of water in the pool is gradually decreasing. Next day, 0.986 times whatever was in there, whoops, plus the 1,000. And then, that's after 3 days, word question, you'd give a word answer. There will be 146,746 litres in the pool after 3 days.